Mr. Saminathan is a consultant and trainer in aluminium and zinc, especially high pressure die casting, cold chamber and hot chamber processes. A full-time professional service since November 2019. Worked in many areas, both inland and overseas organizations, and handled cold chamber machine capacity up to 1,600 ton, and brands like Buher, Fretch, LK, Toyo, Toshiba, UBE, Zytel, HMT, and local brands, and hot chamber machines such as Fretch and Producer. Constructed many HPDC tools in cold and hot chamber process for thin-walled and medium and thick-walled castings. Well experienced in practical as well as in theoretical, acquired knowledge from French and Bulgaria, Germany in tool and process design in aluminum and zinc process of cold chamber and hot chamber. Also supported many OEMs such as Tasco Hydraulics, HP, TVS, Bing Power, Bosch, etc. for the new casting developments, and worked with overseas customers in Europe, USA, Japan, etc. in field of automotive, agri, electrical and electronics, structural, textile, and aerospace applications. Did his diploma in mechanical engineering in 1991 and also completed MBA in operations in 2015. He is also a member of AluCast, NATCA, IIF, GDC Technical Forum. Today is going to talk about the quality assurance and the quality control part of die casting, which is primarily required for any aluminum foundry business to reach the optimum P&L level. Now I request Mr. Saminathan to take us through his presentation. Sir, over to Saminathan, sir.
Yes, sir. Good afternoon to all, and thank you very much for the opportunity given to present the quality assurance and the quality control part of in die casting. So, I like to proceed to go for a presentation.
Yes.
Yep. So, is it visible right now?
Yeah, sir. You can go ahead.
Okay. Yeah. So today topic we will discuss about quality assurance and the quality control for die casting. So what is mean by quality assurance, which is very important for the output of quality output of any casting. So all the planned and systematic activities implemented with the quality system that can be demonstrated to provide confidence that a product will fulfill requirements for quality. So the planned and systematic activities should be there. The defining product and process quality specifications, advanced quality planning, that is APQP, advanced product quality planning, both product and process quality planning. FMEA, the preventive actions to achieve desired quality of the casting, and failure mode and effect analysis. So this is we just I briefed about the quality assurance, as you know already. The quality control, the meaning of quality control mean mostly it is more the inspection aspects of the quality management. In other words, the operational technique and activities to fulfill requirements for the quality, to ensure the process parameters are met out during the die casting process. Here we will discuss about quality assurance for die casting. We will discuss about the following small topics. First, defining the product quality, internal defects, external defects, tools for improving the product integrity, drawings and specification, gauge measurement and testing equipments, process variables, porosity in die casting, which is very important to address in the APQP stage, and the internal porosity and parting line porosity, and pressure take castings, preventive casting defects, and standard versus precision tolerances. Defining product quality mean the definition of the product quality is fitness for end use, The definition will vary from design to design and usually varies for different area of same part. The checklist C81 and C82 from NATCA should be used in the specification specifying quality requirements. Completed this, defining product quality. So the definition of product quality is fitness for end use. The definition will vary from design to design and usually varies for different area of same part. The checklist C81 and C82 should be used in specifying quality requirements. So there are two general types of discontinuities: internal and external. Internal defect can affect the structure of the casting and may or may not be visible on the surface. The internal defect cannot, sometimes we cannot see, sometimes we can see that. So I like to present this. If we go for full mode presentation, only we can see the checklist. Otherwise, from this, we cannot see the other presentation. So that I'm worrying about this because many things I have in the slides. There is a connections with the other slides. So shall I try with the full screen mode? Can you see?
Yes, sir, please.
Now I like to show the checklist. So this is the checklist for the casting product quality specification. So we cannot go through the full data here. So this kind of checklist number C8101 from the NATCA can be used to define the quality, like casting cleanliness, casting surface finish, metal extension, flash or removal, metal extension, flash removal, core holes, and like that, many pressure tightness, flatness, dimensions, etc. So many things are available here. From this checklist, we can use to define the quality. So the another one checklist. This also for casting, specific the casting surface finish, the casting insert, potting line, surface preparation, plating, anodizing, or other specific other special finishing, painting, etc. So NATCA has given many checklists that can be used. There are two general types of discontinuities, internal and external. Internal defect can affect the structure of the casting and may or may not be visible on the surface. So internal defect, what are all the internal defects? It is mainly porosity is the most common type of internal defect. In many cases, internal porosity will have little or no effect on the overall strength and integrity of the casting. When pressure tightness for a gas or a liquid specification is not required, otherwise it is very important. The mechanical strength test is sufficient to qualify quality assurance for casting strength. Wherever the quality requirement asks for leak testing or pressure testing, it is very important to define the porosity level or internal defect. The external defect, commonly hole shed, that is knit lines, we call it as incomplete fill, snills, surface roughness, build up, die loop or soldering accumulations, heat checking, very small risers, fins on part. This is called as hole shed, other defects. That is external defects. External or surface defects do not generally affect the structure of the casting. It can be improved by proper gating design, calculated design parameters, and simulations. Types and severity of external defect depends upon final surface treatment like painting, powder coating, bright plating like chrome. Surface finish standard for die casting are normally developed on a part by part basis between the producer and the user. Checklist C82, already I shown you, that can be referred. As cast surface finish, reference sample standard should be retained by all parties after agreement of the acceptable standard. Refer guideline G66 for surface finish as cast. This is also from NATCA. So I will show you the checklist. This is engineering design additional specification guidelines, surface finish as cast, general guidelines,
If you go through that, you can get the guidelines for the as-cast surface finish as per the grade, utility grade, functional grade, and commercial grade, consumer grade, special grade, etc. And the heat checking occurs during the life of the die when small cracks appear in the casting surface due to thermal cycling, cooling by spray, and heating by incoming metal. Raised fins are removed by shot blasting or grit blast or by vibratory finish on the casting itself. For example, if the dies are used after 50 to 60,000 shots, the heat check mark will develop. It will reflect in the casting. It can be removed by shot blasting or grit blasting or vibratory finishing. The tools for improving product quality. What are all the tools? Two tools can be used. The following tools are used for your typical metal flow simulations. One is PQ square analysis, another is filling simulation. Simulation can be used to optimize the heat flow, determine the location of cooling lines and cooling requirements. Simulation can also be used to predict die distortion, casting ejection temperature, and dimensional capability, last place to fill, and the area of poor fill or non-fill, and pockets of porosity, etc. So simulation can be used to predict this kind of defects in the casting. They also indicate where the overflow should be placed as indicated by the last area of the casting fill. So when we try to place the overflow in the casting, this will show where is the end of the fill. The simulation will give an accurate depiction of the filling process and will verify the suggested gating profile. Many times a runner and gate are cut only to give the results and not in the perfection mode of the desirability. The simulation must be done prior to cutting steel. So here I suggest to use the filling simulation before start the tool manufacturing. So flow and solidification simulation, I can show you some small examples. If you know already also not a problem, I will show here. Engineering should create a 3D model of the casting with the runner and gates connected and export the file in a STL format for the simulation. One example I will show you for the simulation here. Can you see the video? Hello?
Yes,
Hello? Sir. Yeah. I think this kind of simulation already known by the people, but I insist to utilize this without any negligence. So this is the solidification simulation. Here you can see the temperature variation during the solidification. So the yellow color, you can compare the scale in the right side. You can find out the what is the temperature along the all the way during the solidification. From here you can find out which area is solidified first, which area is taking more time, and from there you can plan your quality requirements. So PQ score analysis is one of the methodology to find out the machine capability to fill the material into the die cavity. The PQ square analysis will yield the desired fill time and optimum gate area. The gate depth and the location can be determined for the simulation. So this is the PQ square diagram. Here is the vertical line, is the metal pressure, and the horizontal line is the delivery. That is the cubic inch per second by the machine. This horizontal line is the machine power line, and the inclined. I am moving the cursor. You can see this is the machine power line. From here, you can plot the machine power line, and the horizontal 2 line is the gate velocity limit line, And the another one vertical line is the theoretical filling of the cavity. But this the dotted line is the actual process operating window. This line should cross this window, then only the die is suitable for the machine. If the line is going away from the window, the machine is not capable. This is one type of methodology. It will take more time to discuss. So just I read through for your convenience. A completed PQ square diagram is shown below. Notice that the goal is to predict where a given die will operate when mounted on the machine with a known performance, also shown in an operating window that is developed to match the needs of the casting quality requirements. The objective is to make a design that will have the die and the machine operate within the range of the developed operating window. So by using the PQ square diagram, we can find out whether the tool is can run in the machine or not. Otherwise, what I have to do, you have to go back to the design, you have to correct it until you get the line crossing through the hatched line. And drawings and specification. To ensure uninterrupted production to specification at the most economical level, it is important to supply all drawings and specification to the diecaster with the RFQ. It is necessary that the drawings and the specification contain the following specification. All the drawings should contain mostly 7 to 8 points here. So AQL, what are all the PPM level, the datum location for the machining, what are all the CTQs critical to quality, and surface finish, engineering change note, ejector pin marks, trimming and parting line, non-critical area, standard for approval and rejections. For example, if they left out some of the points, the diecaster should ask the customer to give all the details during the time of RFQ. The drawings and specifications here, I am putting here around 10 points, dimensions or areas that are critical, major or minor importance, and the acceptance quality level, AQL, and parts per million, PPM level, to which they will be checked, including the dimension for which the customer will be requesting control charts. Datum location to be used for machining and gauging, and the areas to be used for special checking. The gauging procedures the customer intended to follow and the special gauge that will be furnished. Special requirements and the area to which they pertain. Coded surface on part to be painted, and designating classifications of surfaces. Indication as to where die trimmed edges are not acceptable, and specifications of degree of metal extension removal required. This is also one type of important point. And you can refer this G65 in the section 6 of NATCA specifications. Indications of any engineering change level requirements by purchase order and accompanying drawings. Specification of those surface which may not be used for location of the ejector pins. A list of generic print tolerances which will adequately describe all the non-critical areas on the printer. Clear descriptions of the all standard for approval. This all points should be specified during the RFQ. Hello? Am I audible?
Sir, yes, sir. Please continue, sir.
Yeah, I will take a few seconds. Proper gauging equipment must be provided for effective measurement of the product conformance. Special gauging requirements should be stated, and the responsibility for maintenance should be tabled on the RFQ. The customer should also furnish complete inspection methods and gauge design information to the diecaster. Sometimes they left out. Why I am insisting these points? It should be addressed during the RFQ and should be addressed in the APQP stage for uninterrupted production of the components. It is recommended that all the gauging to be qualified both customer and diecaster. It is also suggested the gauge R&R should be done on all customer supplied special gauges. A gauge and measurement instrument calibration system record maintained by the diecaster will assure consistent measurement control. The process variables, we will discuss about the important process variables. There are 5 process variables that affect the quality of the casting. Metal analysis, that is the quality of the material, that's composition, etc. The metal temperature, die lubricant characteristics, die filling conditions. In general, die casting is a setup dominant process that exhibits variation of the serial rather than random nature of the 5 variables. Only number 5, that is die filling condition. Die filling condition exhibits the continuous drift variation that the traditional XR control charts were convinced to monitor, that can be used for the die filling conditions. Variable 2 and 3, metal temperature and die temperature. Continuous monitoring should system better united to measure the variability of the temperature related variables. That means you can use the continuous monitoring system. That means some type of thermocouples can be attached to the tooling, sometime in the material, can be used to monitor the 2 variables. Variable 5, die filling condition consists of the element of short profile that short monitoring equipment can monitor and measure. For example, the slow speed, first phase speed, second phase speed, and second phase starting point, intensification starting point, all can be monitored through the machine monitor. This is one type of injection profile and hand drawn by myself during one internal discussion in our office. So here you can see my cursor. This is the constant speed curve. This is a constant acceleration curve. If you use this curve, the right side, a constant acceleration curve, you can evacuate all the air in the short sleeve. So you can reduce the porosity in the casting. That's why I'm showing here. Okay, this is only one important point in the injection profile. Others are normal, the second phase and intensification take 4 points on. The PPM level, since the part complexity, customer requirements, and level of processing contribute to the reject level. Process capability studies may be used to assist in the predicting PPM level for specific castings, secondary process assemblies. Ultimately, the PPM goal or requirement should be as agreed upon between the diecaster and the customer. So the PPM level should be defined properly for all the processes. Porosity. So this is a very major issue in the diecasting. We will discuss more elaborately about the porosity. It is usually necessary to address porosity when specifying the diecasting. While porosity specifications are very difficult to define, generally there are existing guidelines that provide a good starting point. There is a guidelines. Solidification begins at surface of the diecasting and progress to the center, generating 2 distinct zones in each wall sections as shown in the figure 711. So there is this is a figure. You see, there is a porosity in the center area. Can you see my cursor here? I am moving. Hello? Can you see the cursor?
Yes, sir. Yes, sir.
Yeah. So this is how the porosities are forming during the solidification. Here there is illustration. The dense chilled skin. Here the dense skin and the dense chilled skin at the 2 wall. So what happened? The porosity they push to the center. So it creates the porosity. So the skin which has fine grain structure begins at each surface and extend inward to a typical thickness of 0.38 to 0.5 mm. That's why the machining allowance, if you go more than 0.5 mm, the porosity will be exposed to the surface. So only we ask for less than 0.5 mm. this area is usually free of porosity compared to the center of the section. The porosity is located between the skins in the core. The finer grain structure and absence of porosity given the skin superior mechanical properties. So the surface nearer to the wall, to the die, will be more dense than the center and also won't have much more porosity. Skin thickness of the die casting is relatively constant and is not a function of total wall thickness. Therefore, thin wall sections can actually be stronger and more constant than thick sections. So here you can see the skin effect due to rapid solidification in the die. The die casting outer skin has a dense, fine-grained structure with a higher strength than underlying metal. According to Borland and Sumagati, the skin extends inward to a typical depth of 0.38 to 0.5 mm. The rapid solidification of the skin tends to drive porosity to the center of the section as propagated here. Exposing porosity. The removal of the skin to depth greater than 0.5 mm by machining increase the chances of exposing porosity in the core, as can be seen in figure 712. Exterior or surface porosity can be identified with the naked eye by magnifying and penetrant inspection test. This is usually we are doing. The as-cast surface is more dense than the core, and hence stock removal by machining should be minimized. The die caster should be aware of critical area as porosity can be managed to large extent via gating, overflow, chill, and various process parameters. So the porosity standard should be taken care during the die design by proper gating system, properly allocated the overflow in the casting gating system and chill vents. This is the porosity after machining. There is a classification, various degrees of porosity exposed after machining, A, B, C, D, E, F. So you can see this is one type of defining the porosity. NDT method of inspection. Casting can be inspected by utilizing non-destructive inspection technique, NDT, when specified reasonable detection level should be employed. Non-destructive testing method for internal porosity detection, including radiography, X-ray film, real-time ADR, automatic detect recognition, and various weight techniques method. Weight techniques method can be used only for small components, not for bigger components. It cannot be detected. And methods for external porosity detection, including visible and fluorescent dye penetrant DPI methodology can be used. If porosity is a major concern due to leakage or pressure tightness issue, the equipment of a pressure test should be considered like leak testing underwater with specified air pressure, differential air pressure. Two methodology can be used. The underwater methodology, it is a very cheap method. The differential air pressure method is a costly method. Internal porosity. Internal porosity can be detected by a range of techniques, including detection by fluoroscope, X-ray, and ultrasonic procedure. Internal porosity can also be detected in the die casting plant through sectioning and simulated machining techniques when the die caster is advised for the areas to be machined. This usually we are doing in the all die casting plants by cutting the component. Part prints should call out the area where only the lowest level of pinpoint porosity can be tolerated, areas where additional porosity can be tolerated, and area where large porosity will have no effect on the casting application. This all should be noted in the drawing itself. Whether porosity levels are defined by X-ray or sectioning procedure, each party should retain the sample radiograph or part section. Each party being the die caster and the customer. Part section that defines the minimum acceptable standard. We can already I showed the figure 712. It is important that the user not specify the porosity limits that are more stringent than required for the application. It is also usually necessary to establish specific porosity standards independently for each component design. Each and every component design, the porosity standard should be defined. The specification of special porosity detection operations will increase the cost of the casting. If it is necessary, only we can do. Otherwise, it's not necessary. Porosity inspection by cut section. This one exact sample shown here by using the wire cut methodology. See the any porosity available during the production of the casting. Porosity standard. The type of porosity may important in defining porosity standard. A small dispersion of smooth round holes, salt and pepper generally less than 1 mm in the diameter, which are caused by a release of dissolved hydrogen in the molten metal or entrapped gas bubbles in the molten metal, may have a minimum effect on the part strength and will not tend to cause leak. So sometimes the smaller than 1 mm won't give much problem in the strength of the casting. Individual non-grouped pores are generally less than 2 mm in diameter. These types of gas porosity are those not commonly found in die casting. In critical areas of the casting where porosity is a concern, the acceptable porosity is often specified in the following format. So this is one type of methodology to define the porosity, specifying the porosity level. The maximum allowable size of the individual porosity, how much size allowable, and the minimum allowable spacing between the two pores, the maximum allowable density of the pores in defining the area. That means the pores per distance square. For example, 1 square centimeter, how many porosity is acceptable, and the density, spacing, size, everything. For example, a node based on this format may look like porosity specification in cross-hatched marked area on print. Print means drawing. 1 mm maximum porosity, pore size 2 mm minimum spacing between pore, maximum of 10 pores per 12 mm. So what happened here? This is the one methodology to specify the porosity in the casting. Shrinkage porosity, more jagged shaped shrinkage porosity. So this is the shrinkage porosity. You can see more jagged type. So more jagged shaped shrinkage porosity caused by solidification. During the solidification can cause more problem. This is typically a part design related issue and is caused by heavy sections in the casting. So whenever you have a big heavy sections, you have to be cautious about this kind of porosity. Then we can speak with the customer to modify the product design. Shrinkage porosity can be interconnected and may result in leakages. The shrinkage porosity does not have to be visible to cause leakage and is often microscopic in nature. Shrinkage porosity, when exposed, can be larger than the gas porosity. Normally, the shrinkage porosity will be larger than the gas porosity. For instance, a typical specification for larger drilled and tapped bore is less than 2 mm on the first 3 threads and less than 5 mm on the other threads. This is one type of specification. Minimum porosity begins with the upfront planning in the design of the part and die casting die and the management of the heat in both the die and the casting and the injection condition. So this is the shrinkage porosity already shown. Example of radiography. See, you can see this is one type of radiography sample. Example radiograph of a casting with no visible porosity revealed by radiography. This level of soundness is achievable through consultation with your diecaster and good part design, process design and process monitoring. This is acceptable level of porosity. There is a small porosity, but it is acceptable. Example radiograph of porosity that does not impact upon form, fit and function. The user should be agreeable to accepting a specified amount of porosity in areas of the casting where it does not impact a form, fit and function. This is a shrinkage. Example radiograph of shrinkage. This is a very big shrinkage. It's one example. So porosity precautions. What are all the precautions has to be done? So first it has to be process control and monitoring equipment as well as simulation software is best utilized for castings with stringent porosity requirement. If specific porosity will be detrimental to the use of the product being cast, the die caster must be informed of the area that will require special control to reduce the incident of the such porosity. Otherwise, the die caster should ask the customer. This information must be supplied in the detail at the time of RFP so that precautionary measures such as part design, change request, accountability of the higher scrap, or utilization of the special process can be taken in advance of the die design and construction. Since zero porosity is virtually impossible to achieve in a die casting, the size and nature and location of the permissible porosity should be identified by the customer with the agreement of the die caster. The user should be agreeable to accepting a specified amount of porosity in areas of the casting where it does not impact form, fit, and function. You can see already I shown the 712. After this webinar, if anyone needs the data, I will share that. ASTM standard for porosity level. The ASTM non-destructive testing standard E505 provides reference radiograph for inspection of aluminium and magnesium die casting dies. This can be used for the reference. Parting line porosity. It should be noted that some parting line porosity may exist in some die castings. Whenever possible, casting should be designed to avoid parting line on complex functional or cosmetic surfaces. When this cannot be done, special measure will need to be taken, such as adding changes in the parting line, adding a hand removal operation to blend the surface, hand removal operation after the casting. Parting line porosity should not be confused with parting line breakout. You can see here, this is parting line porosity. You can see see the examples. This is the parting line. There is a gate porosity. We call this porosity in the gate, in gate or in the overflow gate. These are all the parting line porosity. This is parting line breakout. That means there is no porosity, but some portion of the materials came out during the trimming operation or degating operation. So the parting line porosity and parting line breakout should not be confused. This is also one type of parting line breakout. The pressure tight castings. So the pressure tight castings, that means the leak requirements for component add to their die design and casting cost and should not be specified
Saminathan sir, nobody is asking any questions. Probably they may ask you
Okay.
or email or phone directly to you.
Okay, no problem. I will clarify it.
Sorry? So, thank you very much, Saminathan sir, for conducting
Yes.
very useful webinar,
Yes, sir.
talking about in-depth subject on porosity, shrinkage, and the types of porosity.
Yes.
Those are all the things eye-opener for all the foundrymen who are running Aluminium Foundry and in generic.
Okay.
Thank you very much on behalf of IIF Chennai chapter for conducting this seminar.
Yes, sir. Okay.
Thank you very much, all the foundrymen. Thank you. Thank you, sir.
Thank you, sir.
Okay.
Thank you.
Thank you.
Thank you,
Thank you
sir.
all.
Thank you.
Thank you. Thank you very much. Yeah. Bye bye.